So we're at 2.4, and this is going to be on average rate of change. This is actually a very important concept, especially for people going into calculus and higher. And I think it's just good to know overall. So it's pretty much about slope. So recall slope is going to be written as y2 minus y1 over x2 minus x2. The second y value minus the first y value over the second x value minus the first x value of a line. So we can find the steepness and slope of a line because a line will have the same slope no matter where you're located at. But what if our graph is not a line? How do we find out its steepness in particular? Let's look at this. This is a quadratic right here, a parabola shaped quadratic. And we don't know the steepness of this. The reason why is because it depends where I'm located. If I told you what is the steepness from here to here, this is very steep. But if I look somewhere else from here to here, this is not as steep, is it? So it depends on where you are at on your graph. If it is not a line will always have the same slope, but not other types of graphs. So this becomes an issue because we still want to talk about steepness and slope, even if it's not a line. So what do mathematicians do when they're confused? Well, it's actually very simple. When they don't know what to do, they always go back to what they do know how to perform. So what I'm going to do is instead of dealing with this crazy mess, I'm going to deal with a line. I'm going to use the 2 points I care about and draw a line through it. This line in particular that I draw through the 2 points that I care about is called the secant line. And the goal is, hey, I couldn't find the slope because it always changes, but I can find the slope if I construct a line inside my function, this secant line. So I construct this secant line, and now I'm going to find the slope of the secant line. The slope of the secant line is the same thing as finding the average rate of change of your function. All right? So how do we calculate this? Well, in function notation, we're not going to use y2 minus y1, x2 over x1 over. We graduated from that. Now we can talk about functions. Y is our f of x. Inputs are just your x values. So the distance between these x values, well, this x value is called a, this x value is called b. So it's b minus a, x2 minus x1. The y values are just the output values of those inputs. So this is y2 minus y1 because this is x2. So if I do my function on x2, that's going to be my y2. This is x1 or y1 because this is x1 thrown inside my function. So that gives me y1. All right. Again, the green line is called the secant line. It's a very powerful idea. Now we can find the slope of the secant line. Again, I call this the average rate of change because on my original graph, even if I found this slope of the secant line, this slope that I've gained is not the actual slope. It's the collective slope from those 2 points. From here to here, this has maybe slope of 3, maybe this has slope of 4, 5, 6, 7, but then I'm trying to find a slope that encompasses all those values using the secant line. That's why I call it the average rate of change. So this is kind of like the general slope between those 2 points. So we can write this, formalize it as f of b minus f of a over b minus a. Some of you guys are going to try to memorize that. That is perfectly fine, but I will warn you, every student that I have worked with who tried to memorize this on the final, they often forget. I would just tell myself y2 minus y1 over x2 minus x1 slope, or outputs over inputs. That's another really good way of thinking of it. It's just outputs over your inputs, but you have to find a distance between the two outputs, and you have to find a distance between the two inputs. Okay? We call the outputs subtracting each other the net change. All right? So let's look at f of x equals x squared plus 2. This is my function. I'm not going to give it to you graphically now. Find the average rate of change from x equals 1 and x equals 4. In your mind, it looks like I didn't give you enough information. However, I gave you a lot. So I gave you 2 inputs, x equals 1, x equals 4. You should know how to calculate the outputs. This is why it's important to think inputs and outputs because you might not recall what the y values are. So here's the solution, x equals 1, x equals 4. I need the output, so we have this notation. F of 4, this is the output, minus f of 1, the other output, over the second input, subtracting each other. x2 minus x1, y2 minus y1. All right, the larger value always comes first for the input. So 4 is minus 1 instead of 1 minus 4 because we want a positive denominator. Okay, and that means this has to be the bigger value for the inputs. The outputs can be smaller, I don't know, but what I plug in has to be the bigger value. So if I calculate the outputs, f of 4 and f of 1, using the function x squared plus 2, I have these outputs 18 and 3. Now I'm going to substitute everything in over here. Now this is a subtraction symbol. Subtraction can be very annoying to deal with. So I'm just going to use parentheses here so I don't mess up. And I get 18 minus 3 over 4 minus 1. This is 15 over 3, which is equal to 5. The average rate of change, or that slope of the secant line, is going to be 5 over 1, or 5. All right? Now, what if I wanted you to find the average rate of change from this rational expression or reciprocal expression at x equals negative 2 and x equals 4? So I have to draw a secant line from there. If I do so, I have f of 4 minus f of negative 2 over 4 minus negative 2. 4 is bigger than negative 2, so it comes first. All right. Now, we need to calculate these two right here, but in particular, I did 4 minus negative 2, so I don't confuse myself. I'm going to distribute this negative over, and it becomes 4 plus 2, which is 6. And then if I calculate the outputs of f of 4 and f of negative 2, I get 1/4 over negative 1/2. 1 divided by negative 2 is the same thing as negative 1/2, by the way. So I have, this is going to be calculated as 1/4 minus negative 1/2 over 6. I'm going to turn this to addition by distributing negative. So I got 1/4 plus 1/2. And now I have to get least common denominators. So boom, 1/4 plus 2 over 4. Add these together, I get 3 over 4 divided by 6. Now I'm going to keep change flip. But first I'm going to write this division symbol as the division symbol I'm used to. Now I keep change flip. I get 1 over 8 as my result. This is my average rate of change from negative 2 to positive 4. All right, we're able to do that on nonlinear functions. That means not lines. All right, now the last topic is instantaneous rate of change. I think this is the coolest concept. We will have questions on this, but it won't be as emphasized as other contexts because this is a very calculus-based option, but you will still be required to know it and do it on assignments. So let's take the example 2x squared plus 4. Find the average rate of change, not instantaneous, find the average rate of change from x equals a to x equals a plus h, provided that a and h are real numbers. Now the moment I use these as my inputs, this is called instantaneous rate of change. All right? So what is this idea of instantaneous rate of change? Let's take any value a on the x-axis, any value, it could be anywhere. I'm going to put it right here. It could be over here, it could be over here. It's just any value a for an any. All right? If a is right here, the output, this quadratic right here, the output of a is located on the function itself, the graph, right here. Now, h is, think of it as a very small number for now. All right? We can think of it as any number, but we're going to treat it as a small number. All right? What I'm going to do is, hey, I'm going to move this by h value, so it's going to be a plus h, and see the output there. Boom. And then I use my secant line and then do the average rate of change. Why is this called instantaneous rate of change though? So the idea, instead of using two values, 3 and 4, and finding the average rate of change between those, I choose a value like 3, and I'm going to choose a very close value to that 3. Maybe the h value could be 0.001. Then that means a plus h is 3.001. So I'm finding the rate of change from 3 and 3.0001. So that's the idea, and this is a very powerful idea. Okay, so it's the same concept, f of a plus h minus f of a plus h minus a. I use parentheses so I don't mess up, by the way. In your denominator, if I subtract this out, combine like terms, minus a, positive a, so it's just h. All right, I need to calculate these outputs. If I wanted to calculate these outputs, again, this comes first because a plus h is bigger. But if I calculate the outputs, I have this squared plus times 2 plus 4, etc. And then I have to FOIL it out. Many of the times you will have to FOIL this mess out. So I FOIL it out right here, and boom, I got this expression and this expression for f of a. Now I plug them in, I distribute that negative over so I don't confuse myself with subtraction. Boom. Combine like terms. These cancel out completely. These cancel out completely. I'm left with this guy. Notice that term 1 and term 2 can both be divided by h. So I can cancel out h to both of them, or I can factor out the h and cancel that way as well. You can do either types of cancellation if you want like to. Just don't mess up. And then I get 2h plus 4a is your instantaneous rate of change. So let me go back into so you guys can understand this. We calculate it all. We can calculate it. But now let me explain more about how this actually works out. So I want you to think of average rate of change as speed in particular. A speedometer tracks a car's speed the moment it points to it. How does it do it? Well, what it does actually is instead of using from point A to point B of the car, let's say a car is driving, instead of tracking when the car was at, let's say, this street to the next street and seeing how fast it went between those two streets, what the speedometer does is chooses a specific part where the car is at and says, hey, I'm going to calculate the closest possible point next to where I pointed at the gun at, or the speedometer at. The speedometer was pointed over here. I'm going to look at the point as close as possible next to it and find how fast he went, or she in particular. Let's suppose it was a guy, all right? I'm going to find out how close these 2 points are. How fast did he go from point A to point A plus H, which should be very close to A. And that should be given, that should tell you the instantaneous rate of change. I'm not looking at from point A to B where they could be far away from each other. I'm looking at from point A and the closest possible point next to A. So close that it's almost instant. Okay? And that ends for today. I will catch you guys later. Take care. Bye.